Once you split them, and then you have one density operator over here and one over here, and you start asking how similar they are, not only does the mathematics get more complicated, you start needing fiber bundle structures, and the actual process for computing them is the same mathematics of gauge theory. You get the same mathematics of gauge theory. And this relationship between the lower dimensional space and the composite space, this is where all this, like if you listen to Eric Weinstein talk about this is all fiber bundle stuff. The funny thing is that I didn't start off with the goal of doing the second law of thermodynamics and real time. I started all this to study fidelity, because like I said before, the crazy thing about all of this is that the fidelity can be computed by looking at the surface, like looking at maximum overlap between purification states.
Yeah.
And the thing that really, so now going back to the triangle and the fact that you can rotate it, what you find is that when you're looking at the fidelity of quantum states, if both of the density operators exist on the same probability simplex, then everything is classical. There's no need for quantum mechanics. There's no need for purification. You just do a classical comparison of probability distributions, and you're fine. Like it's not hard at all. But what happens is that when you get the quantum appears when the density operators have two different eigenbases. So this goes down to the idea of taking the one simplex and rotating it. So now I have one fixed simplex. I have one density operator at a point over here. Then I have another one that's a point over here. So now I'm saying to myself, I'm sorry, go ahead.
Yeah, you went on too quick. So you're saying if there was like, what was the first case where it's like mimics classical mechanics?
When both of the density operators that you're computing the fidelity for exist on the same probability simplex.
Yeah. Now, what does it mean to change the eigenbasis? What does that mean? Like, I know.
Yeah. So in this case, the pure states are the eigenbases.
Yeah.
So the pure states are the eigenbases that represent the simplex.
Yeah.
And so to change the eigenbases is to take the simplex and rotate it. So I can take it. I can do a
What does that mean?
I can do a unitary transformation to each one of these. So remember, going back to what that means, you have a Hilbert space. So remember the standard structure of quantum mechanics. You have the Hilbert space, and then you have the space of operators that are acting on the Hilbert space.
Yeah.
And so the Hilbert space itself is characterized by the symmetry group that maps between all pure states.
Okay.
So remember, I'm sorry, go ahead.
The system, the Hilbert. That's how Hilbert space operates in the first place.
Yes, the Hilbert space itself is characterized by a symmetry group.
Okay.
And for instance, like SU.
So the triangle exists, like, so we're just rotating it. That's what you're saying. Okay, I get it.
Yeah. So specifically, it's like I was saying, like with a qubit, the symmetry group of the Hilbert space of a qubit is SU2.
Okay.
And so that's why you're looking at the Bloch sphere, the visualization of the Hilbert space SU2. And so when you're rotating the Bloch sphere, which is associated with going from a state, you're applying the symmetry group associated with the Hilbert space.
Okay.
And so what that means is that for each pure state, I can apply a unitary transformation on it, and because each pure state can be turned into an operator, a projector, like I showed earlier, then that means that I can always construct a set of orthogonal pure states. Well, I can always do that in either way. I can do that whether it's a projector or not, but there always exists a set of orthogonal pure states. And so the orthogonal pure states, those are the things that represent the simplex. So you need orthogonal pure states to represent a simplex. So those are easy to generate. Then what I do is once I generate one orthogonal eigenstates, so one orthogonal eigenstates that represent a simplex, I can just apply the same unitary operator to each one of those bases, and then that rotates the triangle.
Okay.
And so the thing about which is interesting, is that if the two density operators exist on the same triangle, then everything's classical, everything's simple, nothing's hard. But if I take one triangle and rotate it and have another fixed one, and then one density operator over here and one density operator over here, and I ask you, what is the similarity in information, then everything gets entirely more complicated. This is quantum mechanics. I literally think that you can understand quantum mechanics from this perspective. Like, this emergence is quantum mechanics. This split is quantum mechanics. And the thing that's valuable about this perspective is that because I've diagonalized all of my density operators, that's why they're on these triangles. These triangles represent a classical object. So each triangle in itself, in isolation, represents a classical object. and the quantum appears in the unitary relationship between them. It's the fact that I can split them, which makes it quantum, which is associated with the algebraic structure that I mentioned earlier.
Yeah.
Because the unitary transformations are algebraic transformations. It's the algebraic structure that makes quantum.
Okay.
And so once you split them, and then you have one density operator over here and one over here, and you start asking how similar they are, not only does the mathematics get more complicated, you start needing fiber bundle structures, and the actual process for computing them is the same mathematics of gauge theory. You get the same mathematics of gauge theory. And this relationship between the lower dimensional space and the composite space, this is where all this, like if you listen to Eric Weinstein talk about this is all fiber bundle stuff. And it's closely related to fidelity, quantum entanglement, quantum error correction, the Bohm-Aharonov. The Bohm-Aharonov effect is also done within the relationship between a base space and a fiber bundle structure. Like the richness of this is insane. And as far as I can tell, people are like it's this low hanging fruit everywhere. There's low hanging fruit everywhere, and I have so many calculations and so many things. Like I'm just drowning in possibilities of things to research. I haven't even gotten into the idea of perception and how these things, like I was talking to you earlier, and what I tried to explain in my video on the last video I posted on perception of physics. That not a lot of people didn't watch, but that's okay. Like I tried to explain to you exactly how this is just a matter of perception, because unitary. So the exact same thing I described in that video with the eyeballs is exactly what's happening with this.
Yeah.
So now you're getting into the nature of quantum, because if this split is what quantum mechanics is, then it's all a matter of this perception thing. And like the fruit is so low. The concepts are so simple because I'm treating everything classically. It's just a matter of rotating triangles, spheres and triangles. It didn't require anything more than that. And what I find when I talk to other people, it's just like, I mean, some people, like my co-author, Carlo Coffro, he was so encouraging. He was like, this is like amazing, because it's like this jump from fidelity to thermalization.
Yeah.
It was just by the fact of going like, these are macro states. Like this thing from here to here, the macro state, and I just like asserted that, like, this. What is the nature and the essence of a like Boltzmann's entropy? Like, what's the nature of it? What's the nature of a macro state and a micro state? It's a many to one mapping. You have one thing which represents the macro data, and then you have many things that map to it, and the number of things that are consistent with the macro data tell you about the amount of ignorance, because if only you have is the macro data, then all of the things that appear that map to it have to be treated equally. The more there are, the more ignorant you are. This is entropy.
Yeah.
And to me, it's just like, how do people not figure this out? Like, it blows my mind, man. And I know why it is. It's because when you look at physicists and how they think, a lot like that profession selects for people who think very mechanically.
Yeah.
And so if it's not in the textbook, a lot of them don't think about, or they all cling to math. Like everything has to be focused in math.
Yeah. And like I feel like people who think outside the box, they don't have enough rigor and to go deep into the math, and you know what I mean, like understanding.
Oh no, I know, I understand. Yeah, it's definitely a trade-off.
You have both, you know. That's your strong point in this whole thing. You have.
That's the thing, though, is I'm insanely slow. I don't really have both in the same way. Like these other people I'm talking about, the quickness and speed that they can formulate and compute and do math is like 2 or 3 times faster than me.
I know exactly what you mean. Yeah.
So that means that it's not actually that I have both. I do have the deficit, and I don't know, but I am proficient. Like I do have the proficiency and skills to do the math.
Yeah.
And like my mathematical background, and nothing that differentiates me, I think, from most physicists, is that my background is in general relativity, computational geometry, and quantum statistical mechanics and quantum information, like that. And I've also done work in photonics. So it's like, that is not common to have that big of a spread of experience. And so the reason why the surface of ignorance and stuff is so natural to me is because I'm just applying all the mathematics from differential geometry, what I did my thesis on. So most quantum information theorists are not versed in differential geometry.